Hello, hello. Can you hear me? So instead of writing like this, கொஞ்சம் scroll பண்ணிக்கிறேன் கீழே. Give me a second. Give me a second, gang. I have a lot of fans now. A lot of stadium full of people. இப்போ இந்த ஸ்டடி செஷனோட ஃபக் இன்னும் 3 hours தான் எனக்கு இருக்குது. 3 hours ஒரு பெரிய ஸ்ட்ரீமாக போட்டு ஜிம்முக்கு போகணும். ஜூஜுட்ஸு பண்ண ஆரம்பிக்கணும். Fuck. I want to make like a Sigmund Freud video or some shit. You know what I mean? It's like I have like all of this like interest that I acquired just like living. I feel like யாரும் அந்த டாபிக்ஸ்லாம் தமிழில் அந்த ஹியூமரோட யாரும் கன்வே பண்ணதான் நான் நினைக்கல. I mean, I'm not saying I'm funny. I think everything that I put out right now is extremely unfunny and unproductive. But one day I'll get there. One day I'll get there. almost. I keep forgetting. Some of this shit could be used against me, so I gotta be careful. Okay, let's start where we left off. என்ன பண்ண போறோம்? Independence. Okay, I need to erase all of this shit. Man, a lot of it's just like working on sums, you know. Getting good at math is just like working on sums. It's crazy. At least this is the idea, right? Like I'm going to be working on sums in private and fuck, everything else should be on the public. I don't know who cares about all of these streams. Who the fuck is going to look at this stream and be like, you know what I mean, like do anything, get anything out of it? But anyway, look at the views, bro. 5 people looked at it and thought that was tough. That's all I need. 4 people. Actually, I want to check something. Okay, நான் இனிமேல் தமிழில் தான் பேசணும். அதை நான் மறந்துட்டு போயிட்டுருக்கேன். Only Tamil, no more English. None of this foreign influence on my language. இனியிலேருந்து தமிழ் மட்டும்தான். ஆடியோ செக் பண்ணோம். The good thing is no one in a parkla, so then I can figure it out relatively quickly. I can figure out all of this quickly. 2 hours. Fucking hell, who the fuck is gonna watch that? Live refresh. Title required. This is the title, bro. What do you mean title required? Title required. This is the title, bro. What do you mean title required? Should I? They don't understand the things I say on Twitter. Nah, well, I'm wildin'. Should I?
Fucking nigger.
Okay.
They telling me get off of Twitter.
Nah, well, I'm wildin'.
Fucking nigger.
Okay.
They telling me get off.
Seems about right. I think this could go up a little. I think doesn't really matter. Okay. What am I gonna look at, bro? I actually love doing this. You know what I mean? It's like 5 people, 5 of you niggas like watch this. 5 of my nickcasts watch this. So I'm gonna go this.
But how many V2s? So 6. Okay. Like, now, blank. What's this answer on dependent or independent? Dependent. Why? How do I know those are dependent? How do I know that some combination of V1, V2, and V3 gives me the 0 vector? I know because of that. That's the key fact that tells me that 3 vectors in the plane have to be dependent. Why is that? What's the connection between the dependence of these 3 vectors and that fact? Okay, so here's the connection. I take the matrix A that has V1 in its first column, V2 in its second column, V3 in its third column. So it's got 3 columns, and V1, I don't know, that looks like about 2, 1 to me. V2 looks like it might be 1, 2. V3 looks like it might be maybe 2, maybe 2.5, minus 1. Okay, those are my 3 vectors, and I put them in the columns of A. Now, that matrix A is 2 by 3. It fits this pattern that where we know we've got extra variables, we know we have some free variables, we know that there's some combination, and instead of x's, let me call them C1, C2, and C3, that gives the 0 vector. Sorry that my little bit of art got in the way. Do you see the point? When I have a matrix, I'm interested in whether its columns are dependent or independent. The columns are dependent if there is something in the null space. The columns are dependent because this thing in the null space says that C1 of that plus C2 of that plus C3 of this is 0. So in other words, I can go out some V1, out some more V2, back on V3, and end up 0. Okay, so here I've given the general abstract definition, but let me repeat that definition. So this is like repeat. When the V1, let me call them V's now. V1 up to Vn are the columns of a matrix A. In other words, this is telling me that if I'm in m-dimensional space, like 2-dimensional space in the example, I can answer the dependence-independence question directly by putting those vectors in the columns of a matrix. Then they're independent. They are independent if the null space of A is what? If I have a bunch of columns in a matrix, I'm looking at their combinations, but that's just A times the vector of C's. And these columns will be independent if the null space of A is only the 0 vector, is the 0 vector. They are dependent if there's something else in there. If there's something else in the null space, if A times C gives the 0 vector for some non-zero vector C in the null space, then they're dependent because that's telling me a combination of the columns gives the 0 column. I think you're with me because we've seen, like lecture after lecture, we're looking at the combinations of the columns and asking, do we get 0?
So that's the thing. When it gives 0 vector, that means that's what it means. So let's get a 3-dimensional space. Up. Okay. Let's get a 3-dimensional space, right? When let's take a line. This is gonna be what the fuck? This is gonna be something like 3x, 4y, and 3z. This is gonna be a line like somewhere here, right? This line is represented by this one. But what if instead of 3z, it was just 3x, 4y, plus 0z? Well, it's just gonna, this is gonna be the x, y, z. It's just not gonna show on, it's just gonna be in this plane, right? The point is gonna be somewhere in this plane. and not on the y plane at all. So you can kind of say this plane, wherever it may be, it could be this one, right? And this plane right here is linearly dependent with both of these. Let's say there's another equation like the first one. So that's what it means. So to recap, whatever Gilbert Strauss has to say. Okay, நான் இங்கிலீஷ் பேச கூட தமிழில் பேசுவோம். Okay. AC. So we'll take a matrix A and the solution C. Okay. When it's 0, it's linearly dependent because whatever 7, 8, 9, and this will be non-zero. This is all non-zero, by the way. Right. This will be this matrix right here. It'll be linearly dependent, meaning this matrix would look something like this, going through a same plane or same line. If it's a 3x3 matrix, I mean, it's going to be a 3x3 matrix. Right. Let's actually solve this. I don't want to do the full thing. We can use Python for that, matter of fact. I'm gonna print solve. I need to multiply. Missing B argument. What the fuck? No. You got me wrong, bro. எப்படி மல்டிப்ளை பண்ணுறதுன்னு பார்ப்போம் முதல்ல. Okay, kind of np dot keep so this is fuck 5 by 5 linearly dependent on 4 spans. Bro, look at this is the problem, bro. Look at the shit. Okay, let's visualize. Oh, let's see how it looks. We're finding out a dot product. Yeah, this is like NumPy is fucking gay. Don't use NumPy. I think I'll get one of these. Okay, make a that's the thing. Make a 3D dependent linearly dependent to 2D span. Same visual. So it looks something like, yeah, this is 5D. It's a plot of not a 3D matrix. It's a plot of 5D matrix. So that's why it looks retarded. This will look kind of good, I think. Yeah, this is going to be array number 1. Let's test it out. Still, why is it still retarded? I don't get it. Yeah, still looks retarded for some reason. This is not how it looks, by the way. Why are you gay? What even is this? Why is this negative? Why is this going negative? It makes no fucking sense. Whatever.
Or don't we?
That's the connection, right? But now is what it means.
And now we're giving the official name, dependent if we do, independent if we don't. So I could express this in other words now. I could say the rank, what's the rank in this independent case? The rank R of the matrix in the case of independent columns is?
1 less.
So the columns are independent. So how many pivot columns have I got? All in. All the columns would be pivot columns because free columns are telling me that they're a combination of earlier columns. So this would be the case where the rank is n. This would be the case where the rank is smaller than n. So in this case, the rank is n, and the null space of A is...
rank na nan pathina pa row to or matrix edukrom. Let's say இந்த மாதிரி matrix எடுக்கிறோம். Again உள்ள numbers இருக்குன்னு assume பண்ணிக்கோங்க. இத நம்ம row echelon formல நம்ம reduce பண்ணும்போது இந்த மாதிரி ஒரு matrix வரும் உங்களுக்கு. Whatever, right? So this kind of like decides the rank. If there is the number of zeros in the left side or top right, or whichever way you can like decide to eliminate, kind of like decides what's the rank. Alright, in this case the rank is 3, and yeah, if it's let's say it's a 4 by 3 matrix, well, the last rule that we saw is this is mx, right? This is the row, this is the m is the row, and it's the column, and we are kind of like short-sighted. We are kind of short-sighted by the rows. We need to be a 4-dimensional plane. We don't have that, so this will automatically be a 3-dimensional span. All the solutions could be in 3 dimensions only, right? But if we, let's say we do have like another line of code, but it doesn't have zeros, it still doesn't change. So there's 2 rules we should need to keep in mind. Either it's a 4-dimensional matrix, all of the reduced row echelon form should be zeros on the side, which makes it a 4D span, or yeah, that's the only solution. And the 2 cases which doesn't make it a 4D span, where you have you have something like this, but on the last echelon you have like something like this, right? This doesn't apply, and having a like a I'll just put it down. Having something like this doesn't fly because it's a 4x3 matrix. It can still have a solution. You could still do matrix multiplication on this, but it doesn't like give you a solution. It gives you a 3D span. All the solutions will lie in a 3D plane and not in a 4D plane. So that's the mental connection that you need to make.
Only the zero
before
vector.
moving on.
And no free variables. No free variables. And this is the case, yes, free variables. If you'll allow me to stretch the English language that far. That's a case where we have a combination that gives the zero column. So I'm often interested in the case when my vectors are popped into a matrix. So the definition over there of independence didn't talk about any matrix. The vectors didn't have to be vectors in n-dimensional space. And I want to give it some examples of vectors that aren't what you think of immediately as vectors. But most of the time, this is the vectors we think of are columns. And we can put them in a matrix. And then independence or dependence comes back to the null space. Okay, so that's the idea of independence. Can I just, let me go on to spanning a space. What does it mean for a bunch of vectors to span a space? Well, actually, we've seen it already. You remember if we had columns in a matrix, we took all their combinations, and that gave us the column space. Those vectors that we started with span that column space. So spanning a space means, so let me move that important stuff right up. Okay, so vectors.
Spanning is basically all the possible spaces, or like a physical space vector could like move along. So other span now, same thing. Let's take it. So Messi, it's Messi, ancora Messi. Again, I don't even like. I'm learning with you guys, so don't come at me saying, "Well, actually, you should do research beforehand, dummy." I'm making it up as I go. Best way I can describe myself. You just have to make it up, bro. So let's take a three-dimensional space. If the span is 2D, and we saw, and then reason it can be 2D, that means all the possible vectors can lie, let's say, the bottom. In the room floor, in the room or floor, all the vectors can lie. The vector could be here, the vector, whatever. All the vector could only lie in this. So the vector could be represented. Oh fuck. Back. Could be represented something like. I'm gonna try my very best not to black out the screen. Could be represented as the span could be represented as something like this. Right? Could be represented as something like this. Like, matter of fact, நம்ம ஒரு வீடு இங்கே வரைஞ்சிக்கலாம். Fucking இங்கே வீட்டில் ஒரு ஜன்னல் இருக்கு, இந்த சைடில் ஒரு ஜன்னல் இருக்கு, கீழே இருக்கிறது ஃப்ளோர். Okay, if you can kind of visualize what I'm trying to say. Why does it always fuck it up? Don't fuck it up. Okay, in the கீழே இருக்கிறது வந்து ஃப்ளோரு, இங்கே இருக்கிறதெல்லாம் சைடில். This is actually like really good. Hope it doesn't like trip you out. இதான் இந்த வீடியோட கார்னர், இந்த லைன். So yeah, let's have that screen for the next couple of. I actually like that. This is actually like a. Why didn't I think of that? This is actually good. This is actually good. Okay.
Let me call them, say, V1 up to, I'll use some different letter, say VL, span a space, a subspace, or just a vector space, I could say. Span a space means
B is just the first column in a matrix. You could mathematically see it in that way, or just think of a line
the space
in a polynomial equation.
consists of all combinations of those vectors.
Yeah, combinations, as we saw. Again, it's hard to represent it in a beautiful drawing, but it would look something like this. Oh, I don't want that color. I want this one. If it's like this, you take this one right here and you kind of like slide it on here and you get this vector. You could basically do that to every single thing in the bottom floor. Why didn't no one teach me like that? That's actually so easy to understand. Low key, that's easy to understand. But
That's exactly what we did with the column space. So now I could say in shorthand, the columns of a matrix span the column space. So remember, it's a bunch of vectors that have this property that they span a space. And actually, if I give you a bunch of vectors and say, okay, let S be the space that they span, in other words, let S contain all their combinations, that space S will be the smallest space with those vectors in it, right? Because any space with those vectors in it must have all the combinations of those vectors in it. And if I stop there, then I've got the smallest space, and that's the space that they span. Okay, so I'm just, rather than needing to say, take all linear combinations and put them in a space, I'm compressing that into the word span. Straightforward. Okay. So if I think of the column space of a matrix, so I start with the columns. I take all their combinations. That gives me the column space. They span the column space. Now, are they independent? Maybe yes, maybe no.
yeah, that is a really good point to understand. It could be linearly independent or not, right? So the actual 3D world would look something like, it wouldn't actually look like this. It would look something like so this point goes forever this side, forever this side. This goes forever bottom. This is how the 3D world actually looks like, right? This is just a representation. This one will go in all 6 directions, right? Boom, boom, boom. Yeah, this is how the actual 3D world looks like. So the span of the 3D world would literally mean all, literally like everything of it. So yeah, this just mean when the floor is a span, just means all of these spaces, right? Or whatever the equation kind of like represents. Oh fuck, I can go back that much. Fucking hell, now I'm stuck with this. Fuck, bro. Oh, I should have used this one. Oh, sorry guys, I just have to clean this up really quick. Fucking hell, bro. This is how the 3D world actually looks like. But everything is an illusion, you know. So don't get it twisted, guys. This is how the world works. You need to break out of the matrix, Neo. Okay,
Depends on the particular columns that went into that matrix. But obviously, I'm highly interested in a set of vectors that spans the space and is independent. That means like I've got the
English la kuda irukume. Another this is a span of space that you're eligible to take in the span of time. So yeah, kind of explains it.
right number of vectors. If I didn't have all of them, I wouldn't have my whole space.
Man, I just fought
If I had more than that,
so
they probably
bad.
wouldn't be independent. So like basis, and that's the word that's coming, is just right. So here, let me put what that word means. A basis for a vector space is a sequence of vectors. So I call them V1, V2, up to, let me say, VD. Now I'll stop with that letters. That has two properties. I've got enough vectors and not too many. It's a natural idea of a basis. So a basis is a bunch of vectors in the space, and so it's a sequence of vectors with two properties. One, they are independent. And two, you know what's coming? They span the space. Okay, let me take, so time for examples, of course. So I'm asking you now to put definition 1, the definition of independence, together with definition 2, and let's look at examples. Because this combination means the set of vectors I have is just right, and so that this idea of a basis will be central. I'll always be asking you now for a basis. Whenever I look at a subspace, if I ask you, if you give me a basis for that subspace, you've told me what it is. You've told me everything I need to know about that subspace. Those, I take their combinations, and I know that I need all the combinations. Okay, examples. Okay, so examples of a basis. Let me start with two-dimensional space.
Basis. Yeah, let's actually like listen what the guy has to say.
The space, say example. The space is, let's make it R3.
R3, again, this can be represented as, I mean, the Parker 3D space could be represented as 3D, like R3. If it's a 2D space, this will be R2.
Real three-dimensional space. Give me one basis. One basis is, so I want some vectors. Because if I ask you for a basis, I'm asking you for vectors, a little list of vectors. And it should be just right. So what would be a basis for three-dimensional space? Well, the first basis that comes to mind, why don't we write that down? The first basis that comes to mind is this vector, and this vector. Okay, that's one basis. Not the only basis, that's going to be my point. But let's just see, yes, that's a basis. Are those vectors independent? So that
Are those vectors independent? So let's look at the actual thing. I'll actually paste this one. Okay, let's look at yeah, 3D looks fun, more visual. It's the same thing, guys, same thing. Okay, let's take 3 vectors, 1 0 0 0 1 0, and there's no space, but 0 0 1. All of these 3 would look something like, I'll do it in a different color, would be like here, here, here. These are the bases. So it'd be I hat, J hat, K hat. Again, in the numbers line, complex numbers ning பார்த்திருப்பீங்க இதுக்கு முன்னாடி.
That's like the X, Y, and Z axes. So if those are not independent, we're in trouble.
This is like the basic basis, no pun intended. Let's go.
Certainly, they are. Take a combination, C1 of this vector plus C2 of this vector plus C3 of that vector, and try to make it give the 0 vector. What are the C's? If C1 of that plus C2 of that plus C3 of that gives me 0, 0, 0, then the C's are all 0. Right. So that's the test for independence. In the language of matrices,
Dependent meaning, fuck. Take a look at my girlfriend. Da, 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 da. So this is how the real world actually looks like. Bro, every time I zoom in, it gets zoomed out automatically.
which was under that board, I could make those the columns of a matrix. Well, it would be the identity matrix. Then I would ask, what's the null space of the identity matrix? And you would say, it's only the 0 vector. And I would say, fine, then the columns are independent. The only thing, the identity times a vector giving 0, the only vector that does that is 0. Okay. Now, that's not the only basis, far from it. Tell me another basis, a second basis, another basis. So,
Zero matrix.
give me, well, I'll just start it out. 1, 1, 2. 2, 2, 5. Suppose I stop there. Has that little bunch of vectors got the properties that I'm asking for in a basis for R3? We're looking for a basis for R3. Are they independent, those two column vectors? Yes. Do they span R3? No. Our feeling is no. Our feeling is no. Our feeling is that there's some vectors in R3 that are not combinations of those. Okay, so suppose I add in I need another vector then, because these two don't span the space. Okay, now it would be foolish for me to put in 3, 3, 7, right, as the third vector. That would be a goof, because if I put in 3, 3, 7, those vectors would be dependent, right? If I put in 3, 3, 7, it would be the sum of those two. It would lie in the same plane as those.
Again, the point of that is the rank. When the rank is across the thing is like less than what it is, it fucks you up. It fucks you up bad.
It wouldn't be
bro.
independent. My attempt to create a basis would be dead. But if I take, so what vector can I take? I can take any vector that's not in that plane. Let me try. I hope that 3, 3, 8 would do it. At least it's not the sum of those two vectors. But I believe that's a basis. And what's the test then for that to be a basis? Because I just picked those numbers, and if I had picked 5, 7, minus 14, how would we know? Do we have a basis or don't we? You would put them in the columns of a matrix, and you would do elimination, row reduction, and you would see, do you get any free variables, or are all the columns pivot columns? Well, now actually we have a square. The matrix would be 3 by 3. So what's the test on the matrix then? The matrix. So in this case, when my space is R3 and I have 3 vectors, my matrix is square, and what am I asking about that matrix in order for those columns to be a basis? So in this for Rn, if I have n vectors, give a basis if the n by n matrix with those columns is what? What's the requirement on that matrix? Invertible. Right. The matrix should be invertible. For a square matrix, that's the perfect answer. Is invertible. So that's when the space is the whole space Rn. Let me be sure you're with me here. Let me remove that. Are those two vectors a basis for any space at all? Is there a vector space that those really are a basis for? That pair of vectors, this guy and this one, 1, 1, 2, and 2, 2, 5, is there a space for which that's a basis? Sure. They're independent, so they satisfy the first requirement. So what space shall I take for them to be a basis of? What spaces will they be a basis for? The one they span. They're combinations. It's a plane, right? It will be a plane inside R3. So if I take this vector 1, 1, 2, say it goes there, and this vector 2, 2, 5, say it goes there, those are a basis for, because they span a plane, and they're a basis for the plane because they're independent. If I stick in some third guy like 3, 3, 7, which is in the plane, suppose I try to put in 3, 3, 7, then the 3 vectors would still span the plane, but they wouldn't be a basis anymore because they're not independent anymore. Okay, so we're looking at the question of, so again, the case with independent columns is the case where the column vectors span the column space. They're independent, so they're a basis for the column space. Okay, so now there's one bit of intuition.
That actually like kind of like throws you off. Kind of throws me off. You know what I'm saying? What the fuck is this Jew gonna say?
It's Professor Dave. I want to teach you linear algebra.
Man, these guys are smart as hell. I like these guys. Change of basis.
If M is, we could buy some combination of. Professor Dave here. We can also write our new basis vectors in terms of I and J. U1 equals 1, 0 plus 2 times 0, 1. Which words we want to learn about V prime. We find negative 1/3.
No. This is like a bad mental model to have. So, என்ன பண்ண போறேன்னா change of basis. I need some visual shit going on. Oh, I haven't actually looked at this video. Change of basis. I understand what a basis is, but did he talk about change of basis? Change of basis. Oh shit. It's like a later thing. Okay, let's just like
Let me go back to all of Rn. So where I put 3, 3, 8. Okay, the first message is that the basis is not unique, right? There's zillions of bases. I take any invertible 3 by 3 matrix. Its columns are a basis for R3. The column space is R3, and if that matrix is invertible, those columns are independent. I've got a basis
Invertible
for R3.
meaning just it's a square matrix.
Welcome to our video on vectors and dimensionality. Today, we'll explore a common question. How come a vector in 2 dimensions can sometimes only span a 1-dimensional space? Let's start with some basics. When we talk about vectors in the plane, or are squared, we're referring to arrows with both magnitude and direction that exist in a 2-dimensional space. In this 2-dimensional plane, vectors can point in any direction. When we talk about the span of vectors, we're referring to all possible linear combinations of those vectors. In other words, the span is all the places we can reach by scaling these vectors and adding them together. When 2 vectors point in different directions, like our blue and orange vectors, they are linearly independent. Their span creates a 2-dimensional space, the entire plane. But what happens when 2 vectors
Independent, again, this video kinda is doo-doo. Doo-doo. Straight doo-doo.
So there are many, many bases. But there is something in common for all those bases. There's something...
Again, என்ன இதுக்கெல்லாம் என்ன காமனாக இருக்கு பாப்போமா? Where's my pen? Where's my beautiful pen? For everything to be linearly independent, shit. Let's take a matrix A and the variable C. Right. 1. For this to be linearly independent, should be a fat 0. And 2, the determinant of A shouldn't be a 0, right? And 3, the rank of the matrix should be the same as the column. Rank should be equal to the column of the matrix, and it should be equal. The column, it should be a square matrix. So those are the main ideas.
that this basis shares with that basis and every other basis for R3. And what's that? Well, you saw it coming because when I stopped here and asked if that was a basis for R3, you said no. And I know that you said no because you knew there weren't enough vectors there. And the great fact is that there are many, many bases, but let me put in somebody else just for variety.
Again, guys, and the matter இங்க இருக்கிற valuesலாம் இதுக்குள்ள இருக்கிற values 0-ஆ இருக்கலாம், because end of the day when we like do the row echelon form, we can find out the rank, and the rank is all that matters, right? If the rank is like if the rank is 2, right? If the rank is 2, that means இது வந்து ஒரு 2D plane on a 3D surface. It's like a book on your everyday life. It's like a 2D thing, right? It's like a paper. Paper is 2D, and a thread is like 1D. That's the way to think about it.
There are many, many bases, but they all
Again,
have...
if you like look at a thread, it's still like 3D, but look at how thin, how like thin and like no surface area it has, It has surface area, I know, but this is just a fucking example.
Same number of
Chill
vectors.
out.
If we're talking about the space R3, then that number of vectors is 3. If we're talking about the space Rn, then that number of vectors is n. If we're talking about some other space, the column space of some matrix, or the null space of some matrix, or some other space that we haven't even thought of, then that still is true that every basis, that there are lots of bases, but every basis has the same number of vectors. Let me write that great fact down. Every basis, we're given a space, space. R3 or Rn or some other column space of a matrix or the null space of a matrix or some other vector space. Then the great fact is that every basis for the space has the same number of vectors. If one basis has 6 vectors, then every other basis has 6 vectors. So that number 6 is telling me, like, it's telling me how big is the space. It's telling me how many vectors do I have to have a basis. And of course, we're seeing it this way. That number 6, if we had 7 vectors, then we've got too many. If we have 5 vectors, we haven't got enough. 6 is like just right for whatever space that is. And what do we call that number? That number is, now I'm ready for the last definition today, it's the dimension of that space. So every basis for a space has the same number of vectors in it, not the same vectors, all sorts of bases, but the same number.
Again, ஒரு 2D கேமில் நீங்கள் ஒரு 3D கேரக்டர் வச்சா எவ்வளோ ஆக்வர்டாக இருக்கும். ஸோ இட்ஸ் லைக் தட்ஸ் த சேம் லைக் ஐடியா, ரைட்? நீங்கள் வந்து why is it so ugly, man? Why is my drawings so ugly? Let's delete this shit. I want to keep this. So let's say ஒரு 2D கேமில் வந்து நீங்கள் ஒரு 3D ஆப்ஜெக்ட் நீங்கள் வைக்கணும்னு பார்க்குறீங்க, ரைட்? எவ்வளோ அது ஆக்வர்டாக இருக்குது பாருங்க, பிகாஸ் இன் ரியாலிட்டி it doesn't exist. You know, it's like physics and all of the shit. I don't really understand none of that. But here you go. This is what you asked for, bro. Don't do that.
Number of vectors is always the same, and that number is the dimension. This is definition now. This number is the dimension of the space. Not being 0. Spanning, that looks at all the combinations. Basis, that's the one that combines independence and spanning. And now we've got the idea of the dimension of a space. It's the number of vectors in any basis, because all bases have the same number. Okay, let's take examples. Suppose I take, my space is examples now. Space is say the column space of this matrix. Let me write down a matrix. 1, 1, 1, 2, 1, 2, and just to make it clear, I'll take the sum there, 3, 2, 3, and let me take the sum of all, well, let me put in 1, I'll put in 1, 1, 1 again. Okay, so that's 4 vectors. Okay, do they span the column space of that matrix? Let me repeat, do they span the column space of that matrix? Yes. By definition, that's what the column space, where it comes from. Are they a basis for the column space? Are they independent?
Again,
No, they're not independent. There's something in that null space. Maybe we can, so let's look at the null space of the matrix.
Again, null space, when like 2 lines intercept instead of going on their own way. Right? This space is the null space, I believe.
Tell me a vector that's in the null space of that matrix. So I'm looking for some vector that combines those columns and produces the 0 column. Or in other words, I'm looking for solutions to x equals 0. So tell me a vector in the null space. Maybe, well, this column was that one plus that one, so maybe if I have one of those and minus one of those, that would be a vector in the null space. So you've already told me now, are those vectors independent? The answer is, those column vectors, the answer is no, right? They're not independent, because, you knew they weren't independent. Anyway, minus one of this, minus one of this, plus one of this, 0 of that is the 0 vector. Okay. Okay, so they're not independent. They span, but they're not independent. Tell me a basis for that column space. What's a basis for the column space? These are all the questions that the homework asks, the quizzes ask, the final exam will ask. Find a basis for the column space of this matrix. Okay. Now there's many answers, but give me the most natural answer. Columns 1 and 2. Columns 1 and 2. That's the natural answer. Those are the pivot columns. Because, I mean, we begin systematically. We look at the first column. It's okay. We can put that in the basis. We look at the second column. It's okay. We can put that in the basis. The third column we can't put in the basis. The fourth column we can't, again. So the rank of the matrix is, what's the rank of our matrix? 2. 2. And now that rank is also, we now have another word. We have a great theorem here. The rank of A, that rank R, is the number of pivot columns. And it's also, well, so now please use my new word. It's the number 2, of course. 2 is the rank of my matrix. It's the number of pivot columns. Those pivot columns form a basis, of course. So
again,
what's
pivot columns, same thing. Matter of fact, I'll just உங்களுக்கு எழுதி காட்டினது உங்களுக்கு புரியும் ஃப்ரெண்ட்ஸ். நான் அவ்வளோ ஸ்மார்ட். So this will be the pivot column. Again, it doesn't have to be 1. These will be the pivot columns. You need it's equal to the rank. Right, we have like 3 pivot columns. How do you find the rank? It's when you do the row echelon form. How many non-zero rows do you have? Non-zero rows. That will be the rank. Is equal to 3.
It's the dimension. The rank of A, the number of pivot columns, is the dimension of the column space. Of course, you say. It had to be. Right. But just look for one moment at the language, the way the English words get involved here. I take the rank of a matrix. The rank of a matrix, it's a number of columns, and it's the dimension of, not the dimension of the matrix, that's what I want to say. It's the dimension of a space, a subspace, the column space. You see, I don't take the dimension of A. That's not what I want. I'm looking for the dimension of the column space of A. If you use those words right, it shows you've got the idea right. Similarly here, I don't talk about the rank of a subspace. It's a matrix that has a rank. I talk about the rank of a matrix. And the beauty is that these definitions just merge so that the rank of a matrix is the dimension of its column space, and in this example it's 2. And then the further question is, what's a basis? And the first 2 columns are a basis. Tell me another basis. Another basis for the column space. You see, I just keep hammering away. I apologize. But I have to be sure you have the idea of basis. Tell me another basis for the column space. Well, you could take columns 1 and 3. That would be a basis for the column space. Or columns 2 and 3 would be a basis. Or columns 2 and 4. Or tell me another basis that's not made out of those columns at all. So, well, I guess I'm giving you infinitely many possibilities, so I can't expect a unanimous answer here. I'll tell you, let's look at another basis, though. Because it's only 1 out of zillions, I'm going to put it down and I'm going to erase it. Another basis for the column space would be, let's see, I'll put in some things that are not there. Say, oh, well, just to make my life easy, 2, 2, 2, that's in the column space. And that was sort of obvious. Let me take the sum of those, say 6, 4, 6. Or the sum of all the columns, 7, 5, 7, why not? That's in the column space. Those are independent, and I've got the number right, I've got 2. Actually, this is a key point. If you know the dimension of the space you're working with, and we know that this column, we know that the dimension, DIM, the dimension of the column space is 2. If you know the dimension, then and we have a couple of vectors that are independent, they'll automatically be a basis. If we got the number of vectors right, 2 vectors in this case, then if they're independent, they can't help but span the space. Because if they didn't span the space, there'd be a third guy to help span the space, but it couldn't be independent. So it just has to be independent if we got the numbers right. And they span. Okay, very good. So we got the dimension of a space. So this was another basis that I just invented. Okay, now I get to ask you about the null space. What's the dimension of the null space? So we got a great fact there. The dimension of the column space is the rank. Now I want to ask you about the null space. That's the other part of the lecture, and it'll go on to the next lecture. Okay, so we know the dimension of the column space is 2 in the rank. What about the null space? This is a vector in the null space. Are there other vectors in the null space? Yes or no? Yes. So this isn't a basis because it doesn't span, right? There's more in the null space than we've got so far. I need another vector at least. So tell me another vector in the null space. Well, the natural choice, the choice you naturally think of is, I'm going on to the 4th column. I'm letting that free variable be a 1 and that free variable be a 0. And I'm asking, is that 4th column a combination of my pivot columns? Yes, it is. And that will do. So what I've written there are actually the 2 special solutions, right? I took the 2 free variables, free and free. I gave them the values 1, 0 or 0, 1. I figured out the rest. So, you see, let me just say it in words. These vectors in the null space are telling me, they're telling me the combinations of the columns that give 0. They're telling me in what way the columns are dependent. That's what the null space is doing. Have I got enough now? And what's the null space now? We have to think about the null space. These are 2 vectors in the null space. They're independent. Are they a basis for the null space? What's the dimension of the null space? You see, those questions just keep coming up all the time. Are they a basis for the null space? You can tell me the answer even though we haven't written out a proof of that. Can you? Yes or no? Do these 2 special solutions form a basis for the null space? In other words, does the null space consist of all combinations of those 2 guys? Yes or no? Yes. Yes. The null space is 2-dimensional. The null space, the dimension of the null space is the number of free variables. So the dimension of the null space is the number of free variables. And the last second, give me the formula. This is then the key formula that we know. How many free variables are there in terms of R, the rank, M, the number of rows, N, the number of columns? What do we get? We have N columns. R of them are pivot columns, so N minus R is the number of free columns, free variables, and now it's the dimension of the null space. Okay, that's great. That's the key spaces, their bases, and their dimensions. Thanks.
Bro, look at the amount of people, bro. So depressing. It's like 20 people in the lecture. It's like 20 of them. Okay, I got like 3 of them. 3 of these, and fuck, look at these, bro. This is like the interesting bit. I'm really excited for this one. I need to learn some differential equation for this one. I'm really excited for this one, this one, this one, this one, 4. Yeah, that's about it. Like 4 of them are like really interesting. And here, complex matrices first. Yeah, I think I find it interesting. Singular value decomposition works in a lot of graphic design and all of that. Image compression is really cool. Left and right inverse is pseudo inverse. Transformation and matrix. There's some interesting topics for sure. Yeah, this one's going to be a banger though. Let's watch this. Four-dimensional space. There was this one guy on YouTube, by the way. Let's before we go there. Four-dimensional. Let's just copy this. This is one like 14-year-old kid spreading knowledge. Well, bro, where's that 14-year-old kid? This is the guy, by the way. Visualizing 4D space. Okay, let's see.
We now create a picture that shows how the four fundamental spaces relate to each other and how they capture how a matrix A maps a vector from Cn to Cn. So on the left we have Cn and somewhere
This is
in
liberal
space
propaganda,
is
bro.
X. We know that the matrix A, when applied to X, creates a vector
Yo, we need to break out of the matrix.
which lies somewhere in Cm. Now, it doesn't just lie anywhere, it actually is within the column space. On the left, we have the row space, and we have the zero vectors on both sides, and then we have the null space. And we know that the null space is orthogonal to the row space, and actually we know a little bit more than that. We know that all vectors that are orthogonal to the row space are in the null space, and all vectors that are orthogonal to the null space are in the row space.
What the fuck, bro?
Okay. What that means is that the vector x can be uniquely written as the sum of a vector in the row space, x sub r, and a vector in the null space, x sub n. And we know that the vector x sub n maps to the zero vector in Cm.
What
Alright,
even is
and
going
we
on?
know that a times x n is 0, so we
What
get
the fuck is going on, bro?
a times xr.
What even is
What
this?
that really means is that that vector in the row space
What the fuck is going on? Like,
null space with
Bro.
the column space.
is this like a fucking
And as
Pimp a
well,
Butterfly
all
album
vectors
cover? What
that
the
are
fuck?
orthogonal to the column space are in the left null
Wow,
space, and all of the vectors
interesting.
that are orthogonal to the left null space are in the column space.
Yeah, absolutely.
Now, if the dimension of the row space is r, then the dimension of the column space is r, the dimension of the null space is n minus r, and the dimension of the left null space is m minus r.
What the
This
fuck?
picture captures how matrix A maps vectors from Cn to Cn and how it
Oof.
relates to the four fundamental spaces.
I gotta learn this now. What the fuck? Four fundamental subspaces. Oh, I thought it was 4D. What the fuck? Oh, shit. Did I actually like... I'm pretty sure I saw this video and I kind of forgot it, if I'm being honest. Yeah, I'm like really okay with some of these, but this one, yeah, after all of these ones, like, what am I even looking at? So difficult. Let's do let's just like go into it. Four fundamental subspaces.
Okay, here's lecture 10 in linear algebra. Two
Bro, I'm already in lecture 10.
important things to do in this lecture. One is to correct an error from lecture 9. So the blackboard with that awful error is still with us. And the second, the big thing to do, is to tell you about the four subspaces that come with a matrix. We've seen two subspaces, the column space and the null space. There's two to go. Okay, first of all, and this is a great way to recap and correct the previous lecture, So you remember, I was just doing R3. I couldn't have taken a simpler example than R3. And I wrote down the standard basis. That's the standard basis. The basis, the obvious basis for the whole three-dimensional space. And then,
Bro, what the fuck is going on, bro? Yeah, that's why the examples didn't like make sense. You know what I mean? Like, அதனால தான் அதை பார்த்துட்டு இருக்கும்போதே something is fishy. Something is. Oh, now you can actually see. Oh, I don't actually know. Does it actually improve the stream quality? Probably. Let's go double the speed.
I wanted to make the point that there was nothing special, nothing about that basis that another basis couldn't have. It could have linear independence. It could span a space. There's lots of other bases. So I started with these vectors 1, 1, 2, and 2, 2, 5, and those were independent. And then I said 3, 3, 7 wouldn't do, because 3, 3, 7 is the sum of those. So in my innocence, I put in 3, 3, 8. I figured, probably if 3, 3, 7 is on the plane, which I know it's in the plane with these two, then probably 3, 3, 8 sticks a little bit out of the plane. And it's independent, and it gives a basis. But after class, to my sorrow, the student tells me, wait a minute, that third vector 3, 3, 8 is not independent. And why did she say that? She didn't actually take the time, didn't have to find what combination of this one and this one gives 3, 3, 8. She did something else. In other words, she looked ahead because she said, wait a minute, if I look at that matrix, it's not invertible. That third column can't be independent of the first two, because when I look at that matrix, it's got two identical rows. I have a square matrix. Its rows are obviously dependent. And that makes the columns dependent. So there's my error. When I look at the matrix A that has those three columns.
Yeah, that's an obvious error. Like, yeah, the rank is like, what, 1? So obviously they're dependent.
Those three columns can't be independent because that matrix is not invertible because it's got two equal rows. And today's lecture will reach the conclusion, the great conclusion, that connects the column space with the row space. So the row space is now going to be another one of my fundamental subspaces. The row space of this matrix, or of this one, well, the row space...
You know what's the funny thing? Like, you know, and my college school, but we need to like watch other YouTube videos to like cross-reference the teaching. But when you're like studying alone, even if you're studying alone, you still have to fucking cross-reference all of this with like other people's stuff. Fucking crazy, bro. Fucking liberals.
Space of this one is okay.
They're the problems, you know. We need to. Man, these fucking liberals, man. Fucking pussies.
But the row space of this one, I'm looking at the rows of the matrix. Oh, anyway, I'll have two equal rows, and the row space will be only two-dimensional. The rank of the matrix with these columns will only be 2, so only 2 of those columns can be independent too. The rows tell me something about the columns, in other words, something that I should have noticed and I didn't. Okay, so now let me pin down these 4 fundamental subspaces. So here are the 4 fundamental subspaces. This is really the heart of this approach to linear algebra, to see these 4 subspaces, how they're related. So what are they? The column space, C of A. The null space, N of A. And now comes the row space, something new. The row space, what's in that? It's all combinations of the rows. That's natural. We want a space, so we have to take all combinations, and we start with the rows. So the rows span the row space. Are the rows a basis for the row space? Maybe.
Wait. So what do you mean by... It's still like difficult to like actually wrap my head around what is transformation. Let's ask our friend over here. Who the fuck is this guy?
As you can probably tell by now, the bulk of this series is on understanding matrix and vector operations through that more visual lens of linear transformations. This video is no exception, describing the concepts of inverse matrices, column space, rank, and null space through that lens. A forewarning though, I'm not going to talk about the methods for actually computing these things, and some would argue that that's pretty important. There are a lot of very good resources for learning those methods outside this series. Keywords, Gaussian elimination, and the row echelon form. I think most of the value that I actually have to add here is on the intuition piece. Plus, in practice, you usually get software to compute this stuff for us anyway. First, a few words on the usefulness of linear algebra. By now, you already have a hint for how it's used in describing the manipulation of space, which is useful for things like computer graphics and robotics. But one of the main reasons that linear algebra is more broadly applicable and required for just about any technical discipline is that it lets us solve certain systems of equations. When I say system of equations, I mean you have a list of variables, things you don't know, and a list of equations relating them. In a lot of situations, those equations can get very complicated. When I say system of equations, I mean might take on a certain special form. Within each equation, the only thing happening to each variable is that it's scaled by some constant, and the only thing happening to each of those scaled variables is that they're added to each other. So no exponents or fancy functions or multiplying two variables together, things like that. The typical way to organize this sort of special system of equations is to throw all the variables on the left and put any lingering constants on the right. It's also nice to vertically line up the common variables, and to do that you might need to throw in some zero coefficients whenever the variable doesn't show up in one of the equations. This is called a linear system of equations. You might notice that this looks a lot like matrix vector multiplication. In fact, you can package all of the equations together into a single vector equation where you have the matrix containing all of the constant coefficients and a vector containing all of the variables, and their matrix vector product equals some different constant vector. Let's name that constant matrix A, denote the vector holding the variables with a bold-faced X, and call the constant vector on the right-hand side V. This is more than just a notational trick to get our system of equations written on one line. It sheds light on a pretty cool geometric interpretation for the problem. The matrix A corresponds with some linear transformation, so solving AX equals V means we're looking for a vector X, which, after applying the transformation, lands on V. Think about what's happening here for a moment. You can hold in your head this really complicated idea of multiple variables all intermingling with each other just by thinking about squishing and morphing space and trying to figure out which vector lands on another. Cool, right? To start simple, let's say you have a system with two equations and two unknowns. This means the matrix A is a 2x2 matrix, and V and X are each two-dimensional vectors. Now, how we think about the solutions to this equation depends on whether the transformation associated with A squishes all of space into a lower dimension, like a line or a point, or if it leaves everything spanning the full two dimensions where it started. In the language of the last video, we subdivide into the cases where A has zero determinant and the case where A has non-zero determinant. Let's start with we subdivide into the cases where A has zero determinant and the case where A has non-zero determinant.
Yeah, this is kind of like a place into volume too. So this one is obviously as determinant non-zero. If the determinant was zero, everything will like kinda, this is how it would look. It would look, you know what I mean, you would get like squished into like one. That's how it would look.
Let's start with the most likely case, where the determinant is non-zero, meaning space does not get squished into a zero area region. In this case,
Again,
there will always be
zero.
one and only one vector that lands on V,
Zero.
and you can find it by playing the transformation in reverse. Following where V goes as we rewind the tape like this, you'll find the vector X such that A times X equals V. When you play the transformation in reverse, it actually corresponds to a separate linear transformation, commonly called the inverse of A, denoted A to the -1. For example, if A was a counterclockwise rotation by 90 degrees, then the inverse of A would be a clockwise rotation by 90 degrees. If A was a rightward shear that pushes J hat 1 unit to the right, the inverse of A would be a leftward shear that pushes J hat 1 unit to the left. In general, A inverse is the unique transformation with the property that if you first apply A, then follow it with the transformation A inverse, you end up back where you started. Applying one transformation after another is captured algebraically with matrix multiplication. So the core property of this transformation A inverse is that A inverse times A equals the matrix that corresponds to doing nothing. The transformation that does nothing is called the identity transformation. It leaves I hat and J hat each where they are, unmoved, so its columns are 1, 0 and 0, 1. Once you find this inverse, which in practice you do with a computer, you can solve your equation by multiplying this inverse matrix by V.
That's yeah, it's basically the reverse. So let's actually delete this shit. Let's say we have some sort of object here, and the I hat and J hat is over here, and we want to put this object down here, whatever. We need to actually like change it using the basis vector. So let's say this vector would be this one, this going here, this inverting here. So it would be like, I don't know, like 1, 2, two, 0. Actually don't know, like maybe 2, 0, negative, yeah, -5 or whatever, and the inverse of it would just be this. So when we like actually multiply both of them, we would get 2 multiplied by -10 plus 0. Sorry. I have 2, 0. Well, what am I doing? Oh, the determinant is sorry. It would look something like it would be the exact same thing. Nah, whatever. Fuck it. I theoretically know it. I theoretically what it know what it means.
And again, what this means geometrically is that you're playing the transformation in reverse and following V. This non-zero determinant case, which for a random choice of matrix is by far the most likely one, corresponds with the idea that if you have two unknowns and two equations, it's almost certainly the case that there's a single unique solution. This idea also makes sense in higher dimensions, when the number of equations equals the number of unknowns. Again, the system of equations can be translated to the geometric interpretation where you have some transformation A and some vector V, and you're looking for the vector x that lands on V. As long as the transformation A doesn't squish all of space into a lower dimension, meaning its determinant is non-zero, there will be
So in a 3x3 matrix where there's 3 unknown, I'm doing it. Let's take a 3x3. Bro, I need a fucking break. It's actually like tiring doing this. Kind of like squishes into that. Okay, bro, how long have I been streaming? Should I watch another? Should I watch another one? Should I watch a... Fuck, I'm just gonna take a break really quick and continue whatever that I'm doing. Okay, let's look at linear regression. Okay, I'm gonna just look at some of the important topics. Let's look at this.
Sailing on a boat headed towards StatQuest. Join me on this boat, let's go to StatQuest. It's super
Whoa, that's actually
cool.
crazy, bro.
Hello, and welcome to StatQuest. StatQuest is brought to you by the friendly folks in the genetics one. There's a lot of parts to linear models, but it's a really cool and powerful concept, so let's get right down to it. I promise you, I have lots and lots of slides that talk about all the nitty-gritty details behind linear regression, but first, let's talk about the main ideas behind it. The first thing you do in linear regression is use least squares to fit a line to the data. The second thing you do is calculate r squared. Lastly, calculate a p-value for r squared. There are lots of other little things that come up along the way, but these are the three most important concepts behind linear regression. In the
Interesting.
StatQuest, fitting a line to data, we talked about fitting a line to data. Duh.
Okay. இந்த சைடில் பார்த்தீங்கன்னா mouse size, இந்த சைடில் பார்த்தீங்கன்னா mouse weight. And mouse so it is like directly directly correlated, meaning yeah bro, it's fucking logic.
But let's do a
isn't
quick
it?
review. I'm going to introduce some new terminology in this part of the video, so it's worth watching, even if you've already seen the
It's
earlier
directly
StatQuest.
correlated.
That said, if you need more details, check that StatQuest out. For this review, we're going to be talking about a data set where we took a bunch of mice, and we measured their size, and we measured their weight. Our goal is to use mouse weight as a way to predict mouse size. First, draw a line through the data. Second, measure the distance from the line to the data. Square each distance, and then add them up. Terminology alert. The distance from the line to the data point is called a residual. Third, rotate the line a little bit. With the new line, measure the residuals, square them, and then sum up the squares. Now rotate the line a little bit more. Sum up the squared residuals, etc., etc., etc. We rotate, and then sum up the squared residuals. Rotate, then sum up the squared residuals. Just keep doing that. After a bunch of rotations, you can plot the sum of squared residuals and corresponding rotation. So in this graph, we have the sum of squared residuals on the y-axis, and the different rotations on the x-axis. Lastly, you find the rotation that has the least sum of squares. More details about how this is actually done in practice are provided in the StatQuest on fitting a line to data. So, we see that this rotation is the one with the least squares, so it will be the one to fit to the data.
I think they do it like that's like an example where they do it with like magnets. I think I find that like pretty cool. Not gonna lie.
This is our least
Magnets are
squares
like
rotation,
threads or-
superimposed on the original data. Bam! Now we know why. The method for fitting a line is called least squares. Now we fit a line to the data. This is awesome. Here's the equation for the line. Least squares
But
estimated at 2
why are
parameters.
these guys like so
Y-axis intercept.
monotone? It's like if you know what is in there, just call liberals the lose. You know what I mean?
So what is linear
Just
regression?
call them.
Simply, it's a
call them
statistical
the
method
facts.
where we try to link the input data x linearly into the response y. Let's take a simple example. Imagine you have a product and you want to know how spending money on TV ads.
Morning and welcome back. So what we'll see today, let me show you a visualization of gradient descent and then we'll write out the math. Minus y, which is
Yeah, bro. Good luck learning that. A regression model.
Hi, I'm Adrian Hill, and welcome back to Crash Course Statistics. There's
Bro, she's fucking bad. I ain't gonna lie. I'm a cougar chaser, you know. I like cougars.
something to be said for flexibility. It allows you to adapt to new circumstances, like a transformer is a trunk, but it can also be an awesome fighting robot. Today, we'll introduce you to one of the most flexible statistical tools, the General Linear Model, or GLM. The GLM will allow us to create many different models to help describe the
GLM. Let's look at. Could mean few different things depending on the context you're in. Let me break it down for the most common. Max in statistics. General linear model. General C plus okay, machine learning. In some people casually say GLM, talking about linear models in MLs. Oh fuck. What can I do with all of that data? Let me think. I have like a personal project that I want to do. Look at all of the images. It's all like jitsu positions. I wanna. It's pretty similar, if I'm not honest, but yeah, let's see what I can do with it. Let's see if I can write a script or write a. That would be crazy, because like, let's say I put a picture. I need to write it down somewhere because it's a decent idea. Where should I actually write my ideas? You'll see that. Yo, no, I need. Okay, next stream. I'll take an hour from now. Okay, I'm gonna take an hour and come back.